Yeah. So now you have this minus 1 by 2, this minus 1 by 2, and these are the excited states, plus 1, 3 by 2, plus 1 by 2, minus 1 by 2, and minus 3 by 2. Now you tell me which transition for this particular ground state is not possible for when it goes from minus 1 by 2. For plus 1 by 2, the last transition is not possible, going to minus 3 by 2. But what about this minus 1 by 2? Use the delta mi formula and find it out which one is not allowed. Because question can come in this manner also. Just take the excited state mi value, subtract it from the ground state value. Now here the ground state value is minus 1 by 2. So when I am taking ground excited state as plus 3 by 2 and I'm subtracting minus 1 by 2 from it, what would be the value? Say now my excited state is plus 3 by 2 and I'm taking the ground state as minus 1 by 2. You need to subtract it. What will be the value? Three by 2 minus of minus 1 by 2, 3 by 2 plus 1 by 2 is giving 4 by 2 equals to 2. So when the value is 2, is it allowed or forbidden? Hello? If I'm not audible, please let me know. If you're speaking, you are muted. So is this clear or should I move ahead? Okay, so here I have already explained that in case of excited state, these ones, and if I've taken the ground state as minus 1 by 2, the transition, which is the first transition which we were expecting, minus 1 by 2 to 3 by 2, that is not possible, and it also gives us 3 values. So in total, we will be having 3 transitions from ground state minus 1 by 2, 3 transitions from ground state plus 1 by 2. In total, it would be 6 transitions. So therefore, the answer is 6 transitions. So is this clear?
Clear, ma'am.
So the second question that we had given for the as a homework. So how do we differentiate between the facial and meridional isomers of this particular complex? Earlier we have seen that octahedral, if it is having all the ligands same, that would be having an octahedral point group and the symmetry would be octahedral. That's the highest symmetry, right? But if I'm replacing 3 ligands with L dash, so there is a different second kind of ligand. So in that particular case, if I have put my L, L, and L in this fashion, and the 3 L's consecutively, making a triangle kind of thing. So it's kind of triangle where 3 L's are there, and corresponding to that, this is called as facial isomer. When I have put the carbonyl group at this position and NH3 consecutively, and when we need to find a point group of these isomers, that comes across C3V, because when C3 passes through chromium, all the carbonyl groups, they rotate by 120 degree and give the equivalent orientation. Similarly with the NH3 groups, and it will give you C3V. For the C3V point group, we have seen that one carbonyl is axial and the other two are equatorial. So there would be 2 kinds of CO bands which will be observed by the IR spectroscopy. And the other isomer, if I am placing 2 carbonyls in this fashion and other carbonyl in this fashion, then it would be having a point group of C2V, and C2V point groups give you 3 IR bands because all the 3 COs would be different in this particular case. So whenever there is a question for facial and meridional isomers, you will be having 2 CO bands for in IR and 3 CO bands for, and this is C3V and this is C2V point group. So this is very important question. Any doubts on this?
In facial cardinal group, C3V point group, then meridional CO group is in C2V point group.
That you do not need to mug it up, but you can see directly over here. How are we finding out that meridional is C2V? As I said, that you can see NH3 is here and opposite end NH3 is there. CO is there and CO is here. But in this particular case, if I'll say, this is having at one end CO, another end is C3, NH3. So my C2 has to pass through this one only, so that when it rotates around 180 degree, when it goes around 180 degree, this CO exchange with this CO and NH3 exchange with this NH3, nothing is going to happen on this one. Therefore, it is only having C2V. You're understanding my point? That how it actually happens. So this is the axis which is containing one CO, one chromium and NH3 is passing, and when we are rotating 180 degree, the CO, the axial COs will exchange each other, the equatorial NH3s will exchange each other, and therefore we will get point group as C2. And when we will see the IR spectroscopy, since they are having different dipole, different arrangements around, these 3 COs would be giving 3 signals.
Understood, ma'am.
So then we just discussed the symmetry elements and you already joined at that point. We were revising that how to find out the point group of certain element. Now the main topic for our today's lecture is the character table. So character table is really very important. That could be helpful in many ways in your different exams and everything. So we will start with that particular thing. So, okay, so character table is basically, it's a table which will be having all sorts of, you can get to know about all sorts of applications that you can obtain from group theory. So it's a mathematical table. So generally, if I'll take a normal example, the table would look like, so here there would be, if I'm saying first, this is second, this is third, fourth. This one would be your point group written on the character table. This particular column, it would be having your all classes, different classes of the symmetry elements. And here you will be having Mulliken symbols, of the irreducible representations. I know there are many terms coming. Do not get worried regarding these terms. You will be taking up each thing properly. So this column will be having linear functions like x, y, z, rotational axis, rx, ry, rz. And this would be having your quadratic functions, x square plus y square, x square minus y square, z square, x, y, y, z, zx. Okay. So this is a general form of your character table, how your character table looks like. So generally, if I'll take a simple example of water, we'll explain using the water. So water what is the point group of water?
C2V.
So we have C2V. If you will generally see the point group of C2V, so C2V comprises of what elements? Identity is there. C2 would be there. Sigma, one sigma V would be there. Another sigma V would be there. This is the point group of elements of C2V. Is there any other element in the C2V?
No, ma'am. These four only present.
Yeah. And all these four elements, they are separate. They are four different classes. So what is actually the classes? A class is said to be, when I'm saying that classes, there is a possibility in case of water molecule, we said that E, C2Z, sigma XZ, sigma YZ. So they all form different classes. So there are only four classes and all of them, they are different classes. Whereas if I'll take NH3 molecule, it is having a point group of C3V, right? C3V के elements क्या क्या? It is E, C31, C32, that is also there. 3 sigmas would be there, sigma 1, sigma 2, sigma 3. These are all vertical planes, right? So when we found out that these two, they belong to each other, so that is operation of C3 only. So therefore, it is called as 2C3. That will make you one class. So both these elements will come under one class as named as 2C3. Similarly, these sigmas, they are also coming under one class, so they will be represented as 3 sigmas. Whereas in case of water molecules, this sigma is different class, this sigma is different class. How do we get to know? There is something called similarity transformation. So do you have any knowledge about multiplication table?
Ma'am,
Do you know about the multiplication table of group theory?
largely no, largely not no, ma'am. A little bit no.
Okay. So if you will go back and see what is the multiplication table. So whenever we will be having a similarity transformation says that if I am saying I am taking an element A, out of these I have taken element A, and here is I'm multiplying with some other element and its inverse. So this particular thing, if I'll draw with all the other elements, whatever the combination of values I'll get it, that will come under one class. Say we will take up the multiplication table of this one. Just a second. So this you can see now. Okay. So here we have drawn, I'm taking an example of NH3, that's ammonia. And we know that NH3 sort of like this way. Not a trigonal planar, but yeah, this is not the right way to draw it. So NH3, because it is having lone pair, so it would be here. All the H would be here. So it's a trigonal pyramidal structure, right? So it is having C3V, where one C3 is passing through only nitrogen and all the hydrogens are moving. So therefore C3 is there. And corresponding to one hydrogen, one nitrogen, there would be one plane which is bisecting the other two hydrogens. Correspondingly, we will be having three planes, right? So E is there, C31 is there, C32 is there. What is C33? What is C3? How much rotation?
3, ma'am. 3 rotation.
No, C3 means how much rotation, like what angle rotation you will give.
120.
So when I'm saying it's 3 times, what it would be? 360. Like you have to multiply it by 360, 3 times. 120, then 120, then 120. So it is 360 degrees, right? So when 360 degrees, that is equivalent to E. We already know that
Yes.
whenever I'm
Yes,
saying
ma'am. Yes,
n, how many operations it will give me n minus 1 operations. If I'm saying C3, it will give me 2 operations. If I'm saying C4, it will give me 3 operations. That is C4-1, C4-2, C4-3. But C4-4, C3-3, C2-2, that is nothing but your identity element. So that is already been taken. So clear?
Okay, ma'am. Clear.
And as I said, there would be 3 sigma planes because it's a C3V point group. So sigma V dash, sigma V double dash. So we can consider if it is H double dash, H3 dash. So the plane which is going through NH dash, that is called as sigma V dash, sigma V. And then this is sigma V double dash. Sorry. So I'm taking this as H dash, H double dash, and that is just H. Correspondingly, this one, it would be sigma V double dash. So is this clear?
Clear, ma'am.
Okay. So whatever the number we have kept E, C3, C32, sigma V dash, sigma V double dash. Similarly, along the column also, we have written the same element. And we now have to fill that. So this multiplication table has already been formed. Now, what I was saying that how do we identify which elements are in same classes? So we need to say what number of same classes are there. So firstly, we will check, as I was saying, that how do we find out the inverse first? So if I have to say A into A inverse, it will come as identity always. So this is the rule for finding out the inverse. If you multiply an element with its inverse, it will be giving you identity. So the multiplication of 2 should give you identity if they are inverse of each other. So what we generally say, similarity transformation. To find out the number of classes. So if I'm taking any element A, it has to be multiplied by another element X whose inverse is also there. And this should give you all sorts of elements which should come under one class. So here, if I'll take first element C3, and we will see what different elements will come into that class. So we need to have C3, E inverse, then all the elements, firstly, we will write all C3s 3 times, 6 times. Then C3, C3 inverse, C32. This is another element. C32 ka inverse. Then we have sigma V inverse, sigma V dash inverse, sigma V double dash inverse. So I'm just trying to find out the class, which I was explaining to you, then which elements will come under one class. So I have used this formula where I'm taking an element C3, and in C3, if I have placed C3 in one class, what other elements will come into that class? So X and X inverse. I've taken all the elements and their inverses. Up to this, it is clear?
Clear, ma'am.
Okay. Now looking at the multiplication table, we need to see what is the inverse of identity. What would be the inverse of identity? Identity itself. If you will see, if I am getting multiplying of row into column, E into E is giving me E. So that means E is the inverse of E itself. So I'll be writing in place of inverse E, C3 E, C3 into E, that has to go from left to right. So this would be right to left multiplication. So this is coming as E into C3 again. If you will check, E into C3 will give you C3 only. Clear? So you got first element in the class as C3. Is it clear?
Clear, ma'am.
Now I have C3, fine. Now what is C3 inverse? Go to the multiplication table. Wherever for the C3 table you get E. Where are you getting E? Here. And what is coming here? That means if I'm multiplying C3 into C32, that is giving me E. So C32 is the inverse of C3. Therefore, in place of C3 minus 1 inverse, I will write C32. Here it is C3, here it is C3. When I will write C32, C32, this becomes C3 4 times. That is nothing but your C3 1. Is this clear? Because C33, C34 can be written as C33 into C31 because 3 plus 4 is 1. C33 is identity again, and this is C3. This will give you C3. Is this clear? So we again got the C3. Okay.
Okay, ma'am, I understood.
Now we have taken the element C32, and what is the inverse of C32? We need to check in C32 table. In C32 row, this is the row of C32. We are getting identity underneath of C3. That means C3 is the inverse of C32. Now in place of this inverse, I will write C3 and rest of the things are again same. This is identity. We have already seen that C32 into C3, that will give you C33, that is E, and E into C3 is again C3. Clear?
Clear, ma'am.
Now check for sigma V and its inverse. So we will be seeing sigma V. What is the inverse of sigma V? If I'll check here, sigma V's inverse is sigma V itself. So here, because the multiplication of 2 is giving me identity. Now in place of this one, I'm writing sigma V, C3 into sigma V. First you find sigma V into C3. Sigma V into C3 is giving me sigma V double dash. So I will write there sigma V into sigma V double dash. Now multiply sigma V double dash into sigma V double dash into this sigma V, column into row. So sigma V double dash into row into column, sigma V double dash into sigma V, it is giving me C32, right? So what it will come? C32. So earlier we were getting C3 only, now we got C32 also. That means there is one more element in this class, that is C32. Now similarly, if we'll find for sigma V dash, and here in inverse, sigma V dash ka inverse is wherever it is coming identity, that means sigma V dash is the inverse itself. C3 sigma V dash. What is the multiplication of sigma V dash C3? That is sigma V dash into sigma V. Now, what is sigma V dash into sigma V? That is C3. Sigma V into sigma V dash is C32. So here again, we are getting C32. This also will come as C32. You can find out. So when I applied the similarity transformation, what I got as the answer, when I applied it on the C3, I got C3, 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 C32, C32, C32. So only these two elements, they make one class. That's why I said here that these two come as one class and we have written 2C3. So whenever we form the character table, we will be writing them as 2C3 and nothing more than that. Yeah. Similarly, when we will be applying the similarity transformation for the sigmas, we will be able to get all these C3s, three sigmas will come into one class, and ultimately we will be having the character table. So the character table of C3V will be having E, 2C3, 3 sigma B. So since we got to know one class is this one, if I'll apply for the identity will give you all the elements as identity only. You can try by yourself. If keep the identity element in between and put all the other elements like identity ka inverse, identity C3 inverse, identity C32 inverse, and so on and so forth. When you will find the results, they all will be giving the value as E, E, and E. Therefore, there is one class only for identity, that is single one. Therefore, my character table is having, for C3B, it is having for one class E, second class C3, third class sigma V, where the coefficient 2 represents how many elements are there. C3 class is having C31 and C32, and sigma V class is having all the sigmas. Is this clear?
Clear, ma'am.
Okay. Now we need to find out what are the actually elements that we have to put. So whatever the number of classes you will write over here, the irreducible representations would also be. So number of irreducible representation means irreducible ka matlab, that means which cannot be further reduced. So irreducible representations is equal to number of classes. So that's why my number of rows and columns, they are equal. Clear? Now we need to find out what is the value of this one. So firstly, what we will do, we will take a simple example of C2V, then you can find out for the C2, C3. C2V, we got to know E. If you will find out for the C2V, all these elements, they form their different classes. Sigma XZ, these two planes, they do not belong to same class. That's why we have kept it in other classes. Similarly, we will be having here 4 reducible representations, tau 1, tau 2, tau 3, and tau 4. Okay. Now, what are the rules through which we form a character table? That comes under great orthogonality theorem, which is called GOT. So first postulate, we have already seen that number of irreducible representations is equals to number of classes. So you might be wondering why we are writing number of irreducible representations and what are they. So you notice that when we were splitting the d orbitals and we were giving them as EG and T2G. Remember that? You remember that how we split the d orbitals into EG and T2G?
I know, ma'am.
Sorry?
I know, ma'am.
So what are these actually? How do we get to know that this is EG and this is T2G? How these terminology came? These are actually the irreducible representations. Okay, that's why we are working out the number of irreducible representation and find out what would be actually they're simple. How this E comes, how this T2 comes. Okay.
Okay, ma'am.
So the second postulate says that when we have, just a second. So this Li is the dimension under identity element. So here, whatever the column it is having underneath the identity, say I'm writing L1, L2, L3, and L4. So when I'll be squaring these L1, L2, L3, L4, and then I will add them, that will give me the number which is equal to the order of the group. So what is the order of C2V point group? Order of the point group is nothing but the total number of elements. What is the point group?
4, ma'am. 4.
4, right? So from the second postulate, what I am saying that my L1 square plus L2 square plus L3 square plus L4 square should be equal to 4. You understood?
Understood, ma'am.
So whatever the values it would be here, no? Depending upon that, we name that. Whether it is one dimensional, whether it is 2 dimensional, 3 dimensional. So depending upon that, we name the representations. The first rule says that number of irreducible representations are equal to the number of classes. And second, we found that whatever the dimensions are there underneath identity element column, the squares of those dimensions should be equal to 4. Now we need to find out the values of L1, L2, L3, and L4. How do we find that? First thing, that dimensions can't be 0, can't be negative. Okay, so it can be positive and an integer value. So when we have L1 square, L2 square, L3 square, and L4 square, it is value 4. Firstly, factorize your 4. It would be having 1, 0, 0 can't be the value, 1 and 2. These are the factors of 4. So firstly, we will take up 1 because minus 1 also can't be here. So when I have taken 1, if I'll put 1 square, 1 square, 1 square, and 1 square, this would be 4. So therefore, L1 equals to L2 equals to L3 equals to L4, that is equals to 1. So this is the way to find out the values for dimensions. If I'll say L1 square, L2 square, and L3 square is equals to 6. Say for example, C3B point group ke liye, we have 3 classes and 3 dimensions would be there. Now you tell me what would be the value of L1, L2, and L3. Firstly, tell me what are the factors of 6.
Factors 2 into 3.
Yeah. So also 1 is there, no? 1, 2, and 3. Right? We have this combination. So if I'll say my L1 is 3, L1 3 would be 3 square, that is 9. So we can't even fill anything and it is not even matching because it is 9 and it is 6. So we can't take the L1 equals to 3. So this option is gone. Now take L1 equals to 2. So we took L1 equals to 2. L2 we don't know. L3 we don't know. That has to be 6. So L2 plus L3 square equals to 2 because 2 square is 4. This will come as 2. What do you think? What would be the possible number out of these factors that can be having L2 and L3 and that will give you 2? Three is gone. 2 I have taken. If I'll put one more 2 over here, that will be 2 square. That will be exceeding the value. So what is left? Only one value. So when I will put L2 as 1, L3 also as 1, it will give me 2. So therefore, L1 is 2. Anything else? L2 is 1, L3 is 1. Actually, we go from lower to higher. So we will be taking out the combination as L1 equals to 1, L2 equals to 1, and L3 equals to 2. You got this point now? How are we finding it? Okay. So earlier in this particular table, now we have so now we got this value as L1 equals to 1, L2 equals to 1, L3 equals to 1, and L4 equals to 1. Okay. Now the next postulate says, third postulate says that if I would multiply the coefficient of the element or the class into square of the character, that is should be equal to 4. Say I am keeping this value as A, B, C, D, E, F, G, H, I, J, K, and L. Now I need to find out what are these values. So firstly, what I'm saying is, if this one is 1, and now I have to fill A, B, C, what would be the value? So what we will do, this coefficient is 1 over here, this also 1 over here, 1 and 1. We are saying coefficient into the characters. So whatever we are filling over here, that are the called as characters. Okay. So generally we are putting it like this way. So coefficient is 1 into 1 square. Coefficient is 1 of C2. I'm taking this row A square, 1, B square, 1, C square should be equal to 4. It goes similarly for others also, right? So when we are doing like this way, we get to know what could be the possible combinations which can fill your values, and it will give you a 4 value. So first one we got that it is, we can take first symmetrically as 1, 1, 1. So A value is also 1, B is also 1, C is also 1. So all are symmetric. So ultimately we will be having B2B, E, C2, sigma NC, sigma YZ. This we don't know. 1, 1, 1, 1. So firstly we have to fill it as 4. So we have taken combination as 1, 1, and 1. Now the third rule says, now next rule says that if I have to multiply these two irreducible representations, they should be orthogonal to each other. So the two irreducible representations, they are orthogonal to each other. That means the multiplication of 2 would be giving you 0. So if I'm multiplying these two and their coefficients, that means coefficients into tau 1 into tau 2 should be equals to 0. So what would be the value of D, E, and F? So I'm taking tau 1 into tau 2. Since the coefficients are 1, I'm not considering that. 1 plus D plus C plus F is 0. Similarly, the next one also. So what would be the possible combination that it will give you the 0 value? So it can either take 1 value or it can either take -1 value. It cannot go beyond that, because this 1 and -1, it is with respect to the symmetry. When I'm applying C2 and if it is giving me a symmetric, then it is 1. If it is going anti-symmetric, then it is -1. So it can take only these values. So if I will place like 1, here 1, these have to be -1, -1. That is the only combination which will give me 0. So I'm placing this as 1, this as -1, this as -1. Corresponding to that, we have to place all of them. So if I will place here -1, 1, 1, and -1, -1, and 1. So this table would be filled with all the values when we are having, or when we have applied all the particular postulates. Firstly is the number of classes equals to number of irreducible representation. Second, when we are squaring the dimensions, that should be equal to order of the group. Third one, when we are multiplying the coefficient and the characters, these are the characters of the particular elements, that should be equal to order of the group. And the two irreducible representations should be orthogonal to each other. Now, ultimately, when we see the C2V point group, it is E, C2Z, sigma XZ, sigma YZ. It is giving me value of 1, 1, 1, 1, 1, 1, -1, -1, 1, -1, 1, -1, 1, -1, -1. Is there any doubt regarding this? How are we getting these values?
Ma'am, once again, simply explain here, ma'am, the second irreducible representation in C2V column.
Okay, so here that means this multiplication you're talking about?
Yes, ma'am. Yes, ma'am.
Okay, so this is another postulate where we say that when we have to put the values, like we have 1, -1 values, but there would be many combinations, right? Where we have to put the -1, where we have to put the 1, or why can't this one can have the same values as the above one? So the rule says that when I'm having one full, like this is 1, 1, 1. So the other one can't be having the same value, because then the two irreducible representations won't be orthogonal. So their multiplication has to be 0. That can only be possible when we will shuffle the values. So that's why I say that I was knowing this values, I got to know that it is 1, 1, 1. That is completely symmetric. Like when we are applying these